Big hello from the Tin Man once again. Okay, this is the one a lot of guys have been waiting for. Magnet orientation in the rotors of your Bedini pulse motor. What's good, what's bad, what's best, what's the worst? Most people stick to what the plans say, put the north side out on their rotor. A lot of them are finding that their rotor's becoming, or their core in their coil, is becoming magnetic. The reason because on the pulse motor the coil will fire a north out this side. We've also got the north of the magnet passing the core at the same point, so eventually it's going to become magnetic unless you use carbon or a ferrite, something like that. But the plans call for welding rods. As a member of the TEEP forum posted a link to PESWiki forum, or the PESWiki site, that says use welding rod, which is a softer iron. So the only way we could do this fairly was to do it exactly as per the plan state. Got bifilar wound coil that I made up. It's 20 and 23 AWG wire, that's the plan state. Welding rod for the core, also as per plan. So the way we're going to do this is, I've made 3 identical rotors. As you see, this one I've made with the magnets pointing south out, as you can see. North points to south, of course, opposites attract, which is interesting in itself. That means that our magnetic north is actually at the south pole, so I don't know what actually happened there. So that's all our south out rotor. As you can see, this one's all north out. 4 magnets in each rotor, all the same size, 6 by 12 round magnets. This one here we've made north, south, north, south, yay yay. So we're going to test all 3 under identical circumstances. The first thing you've got to do, make sure you got your coil hooked up right. Now on the plan it says the start of your trigger coil goes to the pot and eventually to the base. The end goes to your transistor on the emitter side. The start of your run goes to your battery and the end of your run goes to the collector. Now depending on which way you wrap the wire around, that can be different. You may actually have to turn the 2 around to get it to push north out like it's supposed to. So just make sure you've done that. As you can see, there's a very strong north out, so we've got that around the right way. So what I've done here, I've got our run battery, and then I've got a cap, large cap here, because I want to measure the amp draw from the run battery, and because this pulse is very quick, meters don't like to take accurate readings of pulses. So we've gone from the negative side straight to the negative on the cap. From the positive side we go through our amp meter and into the cap. So the pulses are being pulled from the cap, and the steady flow from the battery to the cap is going through our amp meter. Our load, another cap. I've put a 460 ohm resistor across it for a load, as well as these LEDs, so we can see that it's actually getting the power. This is off a aerial, flicky aerial off a 4-wheel drive that's snapped. So we've got 2, 4, 6, 8 LEDs in there for 12 volts. Once again, I've fixed the resistance to the base so we can't adjust anything because we want everything to remain as is throughout our test on the 3 different rotors. So we'll go ahead and hook this back up, and of course make sure you get your base and emitter wires around the right way on your pulse coil, otherwise it won't work. Now I've hooked these up like this for a very good reason, and I'll show you that a little bit later on. And then of course the end of your run windings, or whichever one it has to be, so north is out, goes to your collector. We've got our little neon in there, diode off the collector going into the cap. So what we're going to measure with this load is the voltage and the amps. The amps that this is drawing and the voltage that we're getting in this cap with these 2 loads. And then we're going to write it down on each flywheel. And then we can divide up and see what it cost us in amps in regards to get the voltage up. So the first one we'll try is our good old north. You're going to have to bear with me a bit, these are a bit tight on the shaft. Take a bit of wriggling and pushing, worse to get off. So we're all hooked up. At the moment we've got 0.5 of a millivolt in the cap, so nothing. So now we're going to fire it up with our north out magnets. Now once again, because I've got the resistance fixed at 600 ohms, we'll have to wait for it to build up speed, wait for the voltage to settle, the revs to settle, and then we'll write down the results. So looking through the camera, that LED is awfully bright. I'm not doing this any favours really. So I'll cut that off, let that drop down, which will hopefully make things a little better through the camera. Okay, well I know that little one's a little hard to see, but not much I can do about that at the moment. Try this other light. Okay, we're getting close to speed now. So I'm just going to bring this over here. Nope, timed out. So 10.88 volts for 113 milliamps, 10.89. She's just about settled now. So we've got 10.91 volts at 115 milliamps, 10.92 volts. So we'll call it 10.92 volts at 115 milliamps. So milliamps 115, volts 10.92. Okay, I'll stop that one. I'll change the rotor over. Next one we're going to try is our alternating one, north-south, north-south. We'll put that on. Like I said, I made these rotors up this morning, they're all identical in size, all identical magnets. Okay, so our cap at the moment's got, well, it's dropping down but about 30 millivolts. So we'll start this one up and give this one a whirl. Bit of a pain waiting for it to build up speed, but like I said, I wanted to leave everything set so nothing could be changed, and the test was done in identical conditions. At the end of this video, for guys that have gone ahead, spent their money on their rotor, their magnets, glued it all together with north out, and want to change it but don't want to destroy their work, I'll show you how to fix that all so easy without having to unstick your magnets. Oh yes, of course, by the way, each rotor, oh, that's got a lot of voltage going through there. Nearly toasted another neon. But as you can see quite easily, that's the north-south, north-south rotor. That's putting out a very high voltage spike. And if you're looking at the meters, you'll notice the voltage is a little bit lower, but so is the amp draw. It's still picking up speed, another 30 seconds or so we should be right. Okay, I think we're good now. So we've got 10.85 volts. Let's grab my amp meter here. And we've got 93 milliamps. So this one has 93 milliamps, 10.8, 8586, we'll go 85. Okay, that was our north-south rotor. So we'll stop him again. Take this one off. And put our one with all the south out on. Okay. Let's get my leads out of the road. And we'll fire this one up and give her a shot. Keeping in mind while we're doing this, the coil is fixed. The distance between the core and the magnets, that was just a guess. It's about 15 mil at the moment for those small magnets, but they are neodymium magnets, N52s, so they're very strong, so you don't want the rotor too close. Otherwise you will have a lot of cogging effect, and my light's just gone out for some reason. I'll switch back to the other one. Now there's one thing you will notice with having all the south out, and that is your rotor's going to go a little bit slower. And the reason for that is that it's when the coil fires, it's pulling the magnet towards it, not pushing it away, and it only pulses once. If you've seen some of the scope shots of motors with all the north out, you'll see there's 4 or 5 pulses, which can be dropped down to 1 when you trim the pot. So anyhow, I think that's settled pretty much now. So we're on 10.89, 10.9 volts at the load. Now my phone's ringing, so that can just stay there and ring. And our amp draw is 92 milliamps. So we'll plonk that back. We've got 92 milliamps for, it's flickered between 10.89 and 10.9, so we'll go the lower one, volt. Okay, so now we want to know how many milliamps it's costing us for each volt on that load. So we dig out our trusty calculator, wherever I filed that, over this side. And what we're going to do is divide the volts into your milliamps, and that will tell you how many milliamps per volt you're being charged from the run battery. So on our north oriented rotor, we've got 115 milliamps. We divide that by the 10.92, so we got 10.53, that was a pretty good 53 milliamps per volt. So on the north-south rotor we've got 93 milliamps divided by 10.85, that's costing us 8.57 milliamps per volt from the run battery. Now our all south is 92 milliamps, so we divide that by our 10.89 volts. .44 milliamps per volt from our run battery. So our north oriented rotor is costing us 10.53 milliamps draw from the run battery under that load. Our north-south rotor is costing us 8.57 milliamps per volt under the same load, and our south is costing us 8.44 milliamps per volt under the same load. So there you have it. The results are in. Taken me all day to do it, having to make up these rotors and that, but it's something that I wanted to do for the members on TEEP. Now there was one other thing I was going to show you here. For all you guys that have got a beautiful rotor made up, your magnets are glued on so they're never going to come off. We'll go through and we'll put our north rotor back on, like so. Now what you're going to do, good habit to disconnect your run battery first. Take your two trigger wires, swap them around like yay. Of course that's the negative side of my charge battery going to the positive, so we'll have to change that as well. Take your two run coil wires, swap them around, hook up the charge battery to the positive of the run battery again, hook your battery back up, and we're going to check out those results. So there we go. So what you've done in doing that, you are now firing south out this end of your core, north out that end of your core. Now if your core's already magnetised and you're thinking you're going to have to change it, swap it around like that and it'll fire straight up and run better than it's ever ran before. So what we're going to do is we're going to write these results down too and see what this has done. I haven't actually taken results off of this one yet, so I'm not sure myself. Okay, once again you'll notice the rotor runs a little slower because the same effect is happening as was happening with the south magnets. So yeah, this is just for guys that have got a nice rotor made up with north out, your cores are becoming magnetised, that's how you fix it. Swap your two trigger coil wires over, your two run coil wires over. As you can see, runs no worries at all. Alright, so that's settled there. I'd say good enough to get us a result. So we've got 10.991, it's flicking, so we'll put the lowest. 10.9. Our amp draw is now 92 to 93 milliamps, so we're going to go the higher one, we'll say 93. 93. Now we'll do the same as we did with the others. Take our 93 milliamps, divide it by our 10.89 9 bolts. Each volt is now costing us 8.53 milliamps. Now if your core is already magnetised, that will slowly get better the longer you run it. So that's just a fix, simply by swapping your trigger and your run coil wires over. You've gone from 10.53 milliamps draw per volt on your run battery down to 8.53. Like I said, the worst possible thing you can do on a pulse motor is have the north magnets out. So I hope that's helped all you guys out, and you now have the answers you've been waiting for. So until my next video, good luck and good experimenting.